There are some special functions that we need to know their derivatives. And to get their derivatives, of course, the only way we can get their derivatives is to use the limit, guys. Limit definition of the derivative. After using the limit definition of derivative, look at that. We can get the derivative of e to the x function, which is equal to itself, right? Which is so interesting result. This is the only function which its derivative is equal to itself, guys. You need to be careful, okay, when you use that one, okay? It is going to be so helpful, okay, to remember that function derivative. The derivative of e to the x is going to be equal to e to the x. Of course, if you combine with another function, we need to use the chain rule. The second rule is about to look at a to the x. The base is different here in this case, as you see. So if you take the derivative of this function, how are you going to get that one? Of course, you need to use the first rule, also the chain rule, since we know, okay, we can use the logarithm feature and an exponential function features, okay, to get the composite function, and then we can apply the chain rule and then as well as the first rule to get the derivative of a to the x. That's how we are going to use, okay, this special function derivative. And then let's now look at, okay, some example and then also the real world example how we can use them. The first example, I will combine that function by another function which you may need to use the chain rule as well as these rules, guys. Look at the e to the x squared plus 5. I know what is the derivative of e to the x, but I don't know exactly what is going to be the derivative of e to the some function. So if you look at this type of function, as another rule we can give it to you, you see, this is another function. You can just look at here, this is the okay composite function. So here f of x is equal to u, right? The original function is just e to the x. If you apply the chain rule, you would get this one. So I know that the inside function here, right, is e to the x, which is derivative, it is equal to itself, but also I'm gonna need to take the derivative of, right, the outside function, which is f prime x. This is the result of, right, the chain rule, guys. Look at that. I just applied the chain rule here. Now, if I apply the chain rule, right, to my problem, so what it says, look at the chain rule. First, write it down what you have, okay, as it is. So I'm going to do that. E to the x squared plus 5. And then now I need to take the derivative of what I have on the top, which is going to be equal to 2x, the derivative of 5, which is 0. That's it. As you see, right, I applied the chain rule as well as the exponential derivative rule, and then I found it. Another example could be this one, e to the, right, e to the 2x times 3x cubed plus 5x squared. You see, I have, right, the two function, they are multiplied, that's why, okay, I need to use the product rule. Product rule says first take the derivative of this function, first function. We can just separate them in this way. This is f, and then this is the g. If you remember, right, the product rule, that was equal f prime g plus g prime f. That was my product rule. You need to remember. Let me use some different color so that we can remember them. Product rule. So if I apply my product rule, it says f prime is equal to 2 times e to the 2x. Why? I need to apply the chain rule because I have the 2x on the top. The derivative of 2x, which is 2, as you see, the derivative of e to the anything, right? I shouldn't change this, but I should take the derivative on the top term. And then from the product rule, I should keep the g same, 3x cubed plus 5x squared, plus now, right? This is this plus g prime. When I take the g prime, look at that, I'm going to use the power rule, which is 9x squared plus 10x, and then f is going to be same, which is e to the 2x. That is going to be my derivative, guys. Okay, now we are ready to look at some real-world examples. Let's solve an example about the exponential function derivative. In this question, it is asked the risk of the blood cholesterol increases, and then blood cholesterol, okay, were modeled by this function. And then what I am given in this question, as you see, a person cholesterol is 180 milligram, right? So 180 milligram, and also it's going up at a rate of 15 milligram. What is going up? The cholesterol rate over time, so which is 15 milligram per liter. So what I'm asked, what rate is person risk? So the risk over time, right? That is what I am being asked in this question. As you see, the R function, which is the risk function, was not given right with respect to T, which was given by with respect to right the cholesterol level. That is why you need to first right apply the chain rule, since we know that risk can be depend on, which is depend on right the cholesterol level, and that can be calculated over time, as you see. So do I know what that is, which is given here, right, which is 15, and I also need right the derivative of the risk function with respect to cholesterol level, which it is going to be equal 3 times 19, right, times 1006C, and then ln 1006 times 15. This is my derivative, as you see, right, this part, and then 15 is the equal to right the rate of change of cholesterol over time. So if you calculate this number, which it is going to be equal 0.84, something like that, approximately. So as a doctor, your job, okay, is to decide if this rate is right dangerous for your health. Depending on right what these rates are, you need to right adjust your patient medicine level or some other right treatment you need to offer. That's how we can use right as you see the chain rule, and then also since it is modeled by the exponential function, that is how we use right exponential function derivative to get this result about our patient, guys. Another example is about internet user numbers in United States, which is given by the logistic function, a constant here, which is given right as k.0018, and the starting value is going to be 2 million, which is the G0, and then the level out number is going to be 250 million, which is the right of population of United States at that time. So the question here is the growth function of G2 for the number of internet users. So we can find right the growth function using the logistic function. This is going to be our growth function. If you use all these numbers right in the logistic function, if I would like to find out the growth rate right for each year, I need to to take the derivative. Of course, to take the derivative of this function, you need to use the quotient rule as well as the chain rule as well as the exponential function derivative. So just look at the detail, okay, to take the derivative of this one. So as you see, I need to take the square of the bottom, and then I need to apply the kind of the product rule on the top, and then with the minus sign. So when you do that, you are going to apply the chain rule as well as the exponential function derivative. Okay, I found my derivative. Now I'm asking, right, when the year is right in 1995, we can just represent t is equal 5. What would be the value, and then what would be the growth rate? So the internet user numbers is going to be almost right the 17.8 million, but the growth rate per year is 7.4 million users per year. But as we go right, as the time increase, this number, the internet user numbers, of course, will grow, but the growth rate will increase. But after some time, as we might expect from the logistic function, right, the user number is gonna increase, but it is gonna level off, but the growth rate is gonna decrease. Okay, that's how we use the logistic function to model that type of relationship. But as you see, right, how we use right the derivatives, all derivatives rules to get all these information. If you think right, you are the manager of a internet company, of course you need to know right how many users right will join to you next year, so that you can adjust all the expenses for your company for the next year by just looking at all these information, right? That's how we can use to model the real world problem.